integers, they're just powers. So P1R1, that's just a power of a prime. Okay? So again, a power of a prime and so on. Now, these P1 to the R1, they are factors of the order of G. So in a sense I can say the order of G is equal to the I to 1 to k, let's say. This means the product of Pi Ri. Right? And you have k of these. So this abelian group of a given order, a given size, so you know what the size is, you can factorize that number into the product of the powers of primes. Okay? Now that may ring a bell. You probably remember the fundamental theorem of arithmetic. You can take any integer and you can factorize it uniquely into the product of powers of a prime. Okay, so it's sort of analogous. With one big difference though. Here, your primes here, they do not have to be different. Okay, that's rather important. That's the statement of Theorem 39. These primes here can be different, so long as they're factors, right? But they could be repeats. They could be, some of them might actually be the same. Now, I'll give you an example. I've written it out here because it's a bit tedious to write it in real time. Now, let's say you've got an abelian group, and the order of it is 360. So that it has 360 elements. Okay? Now, you can factorize that in terms of the product. This dot here just means times, multiplication sign. Okay? So this is the product of powers of primes. Now that's one form, right? If you work that out, it's 360. Now this theorem 39 says your primes here do not have to be all different, right? You can have some repeats. Well, look, you can rewrite this as this, right? You've expanded your 3 squared to just 3 by 3. And that form is of this form. Well, yeah, this, right? In fact, this is a kind of shorthand. When you see this, think of this as just this. So the z's are missing. The dots here, you translate them into the multiplication sign of a direct product, right? So if you put in the z's, so this pi would be that 2, and the r would be that 3, and the p2, the second prime, would be that one, and the r2 would be that, okay? And imagine the z's in front each time, and the dots you put an x, so you get it in this form. So this is a sort of shorthand form for this, right? Well, it works out, for this particular example, there are like 6 different ways, 3 by 2, 6 different ways you can expand this product of factors, if you like, right? So here they are. Now, what Theorem 39 says, and there's no proof, just give you a taste, right? Theorem 39 says each of these, which is of this form, so each of these groups, a multiple direct product group of this form. Well, these are primes, and these are powers of primes. The r's are powers. So each of these is non-isomorphic. Okay, that's what Theorem 39 says, and you can prove it. That each of these groups, of this form, each of these 6 are mutually non-isomorphic. There is no two of these 6, that is isomorphic. They're all different groups. Remember, if you have two groups that are isomorphic, they're really just the same group. From the point of view of a group theorist, two groups that are isomorphic are the same group. Okay? So these 6 groups here, of this form, they're all different. None of them are isomorphic. But, and here's the interesting thing, any group of this order will be isomorphic to one of them. Okay, got that? So let me sort of summarize a little bit. You take a finite abelian group. You get its order. How big is it? How many elements does it have? You then factorize that order, that number, into all the various ways you can expand these powers of the primes. You break this up into its primes. In this case, we've got 6. All of those groups, this is just shorthand for this, remember? All of those 6 groups, they will all be mutually non-isomorphic. There are no 2 in this group that are isomorphic, right? But that group that you started with, your G, it will be, according to Theorem 39, it will be isomorphic to one of these. One and only one. Right? It can't be isomorphic to 2 of them, because if it is, that means 2 of these are isomorphic. If group A is isomorphic to B, and group A is also isomorphic to C, therefore group B and C are isomorphic. Right? So this group G can only be isomorphic to one of these. Okay? Alright, now so now I can move on to, and we'll do some applications of doing this kind of thing, of factorizing and finding what groups are isomorphic to a given group that you start with. Alright? Now, a few little things I've thrown in which will be useful for when we come to problem solving time. If these integers m and n, if they are mutually prime, I assume you remember what that is, so if m and n are mutually prime, then this product group here is isomorphic to this group, where the modulus now is mn. Okay, so that's useful, and we'll actually use that kind of thing in the problem solving. And these groups they commute, right? So z of m direct product z of n is isomorphic to z of n direct product z of m, right? So you have this. So both of these are useful. All right, now theorem 40. If you take your group and you're trying to find what other groups are isomorphic to it, right? So you just start with some random abelian, finite abelian group G, right? And you if when you factorize it, if you get something of this form, where these D's they are the modulus, right? So if you're able to create a multiple direct product where these moduli here are such that like D1 here divides into D2, so D1 is a factor of D2, and D2 is a factor or divides into D3, and so on. So if in general Di divs or divides into the next one, D of I plus 1, for all the way through, if you can find that multiple direct product of this form, where each modulus here divides the next one all the way through, if you can do that, then this multiple direct product is that's what Theorem 40 says, then that multiple direct product is isomorphic to your group that you started with, G. Okay? All right. Well, that's the end of that session. The next part will be problem solving. So, I guess you're getting a feel. So you can take a group here of a given order, and you can show that it's isomorphic to this form. So using this kind of thing, you can begin to classify your finite abelian groups, and pure mathematicians love to classify things. I mean, it's very nice to know, like, here's the complete list of this type of group or whatever, right? And we can then prove that that list is complete. So it's sort of a nice tidy feeling. You feel you've really mastered something. Okay? Now you may ask the question, and we'll come back to it a bit later. If you have a group of a given order, then how many different, meaning non-isomorphic, how many different groups have that order? Now that's an interesting question, and we'll come back to it later. Like the trivial group that consists just of the unit, how many different groups, non-isomorphic groups, of that form? Well, there's only one, right? That's why it's called a trivial group. So if you have a group of order 2, how many different groups can you have? Well, you think about it and you get an answer. If you have of order 3, 4, 5, 6, 7, 8, and in the text I think we go up to, what was it, 32 of order, the order of the group 32, hold on, let me just check. Groups, only up to 8. So chapter 15, lecture 15, when we come to it, we will discuss all possible groups, non-isomorphic groups, of orders up to 8. Right? So we'll be systematic. Okay, I'll stop there. The next session will be problem solving. And I'll try to cool down a bit. It's very hot right now. Ciao.